Hey everybody, thanks for coming. So my name is Kai Rothog. I'll be talking about Alchemist today. This is joint work with Alex Gittens and Michael Mahoney. Alex is at Rensselaer Polytechnic. Michael Mahoney is at UC Berkeley with me, and he's around in case you want to ask him questions later. And this project was done in collaboration with NERSC and Cray. So I hope it's not too presumptuous of me to assume that everybody here knows what Spark is about. But it's possible that few of you know what MPI is. It was mentioned earlier in the keynote presentations. But basically, MPI stands for Message Passing Interface. And it's not a framework or some software library, it's a specification. It's a specification that's based on the message passing parallel programming model. In this case, you've got cooperative operations between processes, and data can be moved from one process to another. So the key point here is that communication can happen between processes at any time. This contrasts with the bulk synchronous model of Spark, where you have communication at the end of the stages only. So MPI is a dominant model used in high-performance computing. This is in particular the case with scientific computing. They rely very heavily on MPI. You require an installation an implementation of MPI, such as MPICH or OpenMPI. It's considered to be fairly low level. So it's not on the socket level, but it's one level above that. Basically what it gives you is very efficient implementations of collective operations like broadcasting and reducing. Initially, when it was first developed back in the 90s, it was geared towards distributed memory, but these days it can do anything, it can shared memory, GPUs, and so on. Communication for the standard MPI implementation is using TCP. But if you have specialized network protocols, then you can do that. Then you can use that as well with MPI. So the big drawback of MPI is that it does not give you fault tolerance or elasticity, which is one of the strengths of Spark. So Alchemist basically is a product. It started as a case study. People at NERSC, RISE-Lab, and Cray were interested in looking at how linear algebra performs in Spark versus MPI. This is so each organization had its own reasons for doing this. At NERSC, they want to use Spark for data-intensive scientific computing, scientific analysis rather, and at RISE-Lab, the interest was more academic. It was more about just being interested in seeing how well does Spark do linear algebra. At Cray builds supercomputers and provides software to run on them. Their customers want to have Spark available on Cray machines. So Cray, of course, wants to know what can Spark do and what does it need to improve on to run more efficiently on their machines. But there are more general reasons to want to do linear algebra in Spark anyway, and that's because of all the reasons you want to do anything in Spark, which is a fast development cycle. You've got simple dataset abstractions, a whole ecosystem you can use for data analysis before and after the computations, and of course, as I mentioned before, fault tolerance, elasticity, that kind of stuff. The problem is that MPI is going to be more efficient when it comes to large-scale numerical linear algebra computations, and I'll show you why in a minute. So these computations that I'm about to show you were done on a NERSC supercomputer. It's called Cori. It's located at Berkeley Labs. It's got 2,388 compute nodes. Each node has 128 gigabytes of RAM and 32 cores. And in this paper that you see the reference below, it's a wide range of matrix factorization techniques were looked at. One of those was a truncated singular value decomposition, which is a very important numerical technique in a wide range of applications. So data sets, as I mentioned, our emphasis is on large-scale data sets. The data sets we looked at were some ocean temperature data, which was a 2.2 terabyte set, and atmospheric data, which was 16 terabytes. So we performed the singular value decomposition on both of these data sets. If we just compute the first 20 singular values of the 2.2 terabyte set, we have these times here. So what you see here is the amount of time it takes Spark to perform the computations on 100 nodes versus MPI on 100 nodes, and we did this for 300 and 500 nodes as well. So the orange and purple bars, those are Spark overheads. The light blue and blue bars, those are the actual compute times. So you can see here that the Spark overheads actually dominate the compute times, and as the number of nodes grows, the overheads increase. And if we now go to the 16 terabyte data set, we see it's even worse. I mean, if you look at the y-axis, it's a logarithmic scale. In this case, the overheads, those are the bars on the right, the orange and purple ones, they're those overheads completely dominate the actual compute times. So this is a drawback. So this is the reason why linear algebra in Spark is not very efficient. So the lessons learned from this study is even with favorable data, Spark is still 2 to 26 times slower than MPI. And the overheads are the reason for this, and they can be an order of magnitude more expensive than the compute times. Plus they anti-scale. So the larger your data set, the larger the overheads become as well. They grow disproportionately to the size of the data. So this is the reason why we decided to try to interface between Spark and MPI. And that's how Alchemist was born. So our goal is to interface a Spark application with existing or custom-made MPI libraries for large-scale linear algebra and machine learning applications. I want to emphasize here that our goal is not to write our own MPI-based codes, but just make everything that's out there accessible to Spark. So the idea, therefore, is to use Spark for normal data analysis workflow. So that's a pre-processing, cleaning up the data, doing some simple computations that aren't too intensive. But once you have a large data set that requires a numerically very intensive computation, then you want to call some MPI-based code using Alchemist. So the idea is then that you transfer a data set over to Alchemist, which calls a relevant MPI-based codes, and then it sends the results to Spark. So the goal here is then to combine the high productivity of Spark with the high performance of MPI. So I want to emphasize this point. It's about combining the best of both worlds. The high productivity of Spark gives you everything that you need to analyze data efficiently, and the high performance gives you the ability, the high performance of MPI gives you the ability to perform numerical computations where you have to. So the target users of Alchemist, the scientific community is pretty interested in using Spark, but because of the previous results, it just hasn't had good results so far. If we can enable the scientific community to call MPI-based libraries for the analysis of scientific data from Spark, then that's going to make Spark a whole lot more attractive to them. But also machine learning, people working in machine learning and data analysis, they can benefit from this as well. Just the example of the singular value decomposition that plays a key role in machine learning, for instance, in principal component analysis, recommender systems, leverage score computations. Also, in reinforcement learning, when you want to run a bunch of simulations to train your system, you want to be able to call efficient MPI-based libraries just for that as well. So the basic framework for Alchemist is we have a core Alchemist system that acts as a bridge between your Spark application and the MPI libraries. So the way it communicates with the Spark application is by using a client interface. The client interface provides the API for the user and communicates with Spark for the moment using TCP/IP sockets that may change in future. And Alchemist also communicates with the MPI-based libraries with the use of an interface, in this case, the library interface. The library interfaces are written as shared objects, so they import the MPI-based libraries, and then they get loaded dynamically at runtime by Alchemist. So that means you only load the libraries you actually need in your application, rather than just every library that's out there. So the library interface provides a generic interface for Alchemist to communicate with this library. The basic workflow then would be that you have some distributed data set in Spark, for instance, an index row matrix, and you want to perform some large-scale numerical lineage computation on that, for instance. So you send that data over to Alchemist using those sockets. And you also tell Alchemist which function, MPI-based function, and which MPI-based library you want to be using for your computation. And then Alchemist loads the required library, calls the function, and then sends the results to Spark. Of course, if you don't want to, you don't have to send the data directly to Alchemist from the application. You can also load data from file, for instance, HDF5. So inside Alchemist, once we have data either sent to us from Spark or loaded from file, we need to store it in a format that's appropriate for whatever MPI-based libraries we're working with. So there are different candidate MPI-based libraries that we can use for storage purposes. One of them, the most popular one, is Scalapack, but there's also a more recent Elemental library that provides a very convenient interface to storing and interaction with distributed matrices. And for that reason, for this convenience, right now Alchemist is using Elemental, but we're working on supporting Scalapack as well, because that would enable us to support a wider range of MPI-based libraries. So here's a very simple example of Alchemist in action. So in this example, we've got Alchemist running on 10 nodes. 9 of those are worker nodes. And let's say we've got some Spark application 1 in this example, that runs on 4 nodes. 3 of those are worker nodes. So this Spark application decides it wants to use MPI-based library A and C. So, and it wants to do those computations on 4 Alchemist nodes. So what it does is it tells Alchemist that it wants to use 4 of its nodes. The Spark workers then send the data from the application to Alchemist, specifically to those 4 nodes that have been allocated for this application. And these worker nodes then load those libraries that the Spark application wants and perform the computations. And now while this is happening, let's say there's a second application that wants to use Alchemist and perform some MPI-based libraries computations. So in this case, so in this example, that second application only has 1 worker, but it requests 3 Alchemist workers for the computation. So it sends the data over to Alchemist, to those 3 workers. Those 3 workers can load that library C and perform the computation. And then once the results are ready, they get sent back to the application. So in this example, none of the applications use library B, so there's no reason to load it dynamically at runtime. And here's a very elementary example of the API. So in this example, what we're doing is we want to perform a QR decomposition, which is a different type of numerical linear algebra routine. So first what we have to do is import Alchemist. So specifically this is the client, Alchemist client interface, but we're just going to call Alchemist here. And we need to call something called an Al matrix, which is, of course, short for Alchemist matrix. And we need to import the library that implements this QR decomposition. So if it hasn't been done yet, we need to instantiate an Alchemist context object, similar to what you would do with the Spark context object. We need to register this library and give Alchemist the location of the library interface. Remember, the library interface is a shared object. So if it's not an Alchemist repository, then you should give the path of the location of a shared object. So what happens then is that you send the data that's inside an indexed row matrix called A in this example. You send the data to Alchemist simply by creating an Al matrix instance. And you do that by saying Al matrix of A. So what's happening behind the scenes here is that all the data inside A is sent over to Alchemist. And then once that's done, you can call the QR decomposition function on this matrix handle A. So LA here is a matrix handle that tells Alchemist what matrix to do the computations on. You perform the QR decomposition, and you get two matrix handles returned to you, LQ and LR. Now at this point, you could call Alchemist to do additional stuff. Maybe, for instance, you want to do some extra computations on LQ, then you would call another function. But if you're ready to get the data back to the Spark application, then you just say LQ to index row matrix. At this point, the data gets sent from Alchemist to Spark. And then once you don't need Alchemist anymore, you just stop the Alchemist context object. So a couple of examples just to show Alchemist in action here. Matrix multiplication is a very difficult, surprisingly difficult operation to do in a distributed setting. And it's something that Spark isn't particularly good at. That's because the matrices are row partitioned. For matrix multiplication, what you really want to have is one matrix being row partitioned, the other one being column partitioned. That's just because of the nature of matrix multiplication. So this requires an all-to-all shuffle, and in our experience it actually is very difficult and usually fails in Spark once you have data on more than one node. So if we just have a compare the times it takes to do these matrix multiplications in Spark alone and Spark using Alchemist, then we see a vast improvement. So for small matrices that fit on one node, Spark can handle that, but it's still significantly more expensive than Alchemist. And notice here that the total time for Spark plus Alchemist includes both the communication time and the compute time, whereas in Spark it's just the computation time. So on one node, Spark is significantly slower. On more nodes, in this example we have 2 nodes and 4 nodes, Spark actually fails. That's during the all-to-all communication phase. Every simulation we've run, it ended up failing. So that's one example where you can have a significant improvement by using Spark in conjunction with Alchemist. Another example is the truncated singular value decomposition. In this case, we compute the first 20 singular values of some random matrices. These experiments were done on Cori, so at NERSC supercomputer I mentioned before. And we looked at different matrix sizes. We always had 10,000 columns, but different numbers of rows. So what you see on the top right here is the total execution time for Alchemist. So in blue, we've got the transfer times. and green the compute time, and then red, the orange is the time it takes to send the results back to Spark. So what you take home message here is that the overheads, which are these communication times, the blue and orange on the top right, in the top right diagram, they're significantly less compared to the overheads that Spark has. Just as a reminder, the orange and purple bars here, those were the Spark overheads. So not only were they more expensive than the compute times, but they get worse as in this example, as the number of nodes increases. So this contrasts those overheads with these ones here, and you see a big improvement. On the bottom right, we've got the total execution times for Spark with Alchemist. Those are the dark blue bars compared to using Spark on its own. And except for the smallest matrix, we had Spark taking longer than the 30 minutes that we allocated to these jobs. So again, there's a huge improvement here in the total execution times for this application. I also want to see how this scales. I mean, the whole point of doing large-scale computations is you actually want to see that it scales well, so that if you have terabytes of data and data sets are getting larger by the day, you want to make sure that the overheads don't grow at a disproportionate rate. So what we did in this experiment is we took the 2.2 terabyte data set and we replicated it a certain number of times. And we see that the overall execution time remains fairly constant as the size of a data set grows. Now in this example, we actually loaded the data from HDF5 just because there was no reason to load it into Spark and then send it to Alchemist. So it would have taken too long. But in those examples, we loaded from file. The computation times remain fairly constant. Those are the red bars. The green bars are the time it takes to send data back to Spark. In this case, we sent data, I think, to just 2 Spark nodes. That's why you see the total communication time increasing slightly, just because there's more data being sent to just 2 nodes. There's only so much data you can store efficiently. So yeah, this basically shows that using Alchemist, you can achieve weak scaling, which is something you definitely want to have when you work with large data sets. And again, compare the overheads for, in this case, 16 terabyte data set in Spark, where the overheads were an order of magnitude larger than the actual compute times. So we're heavily developing Alchemist at the moment. There are a bunch of things we're working on. One is the Python interface, so you can use Alchemist with PySpark. And at some point, we're also going to work in an interface for R. We're working on supporting sparse matrices. Right now, we only have dense matrices, but sparse matrices are going to be ready soon. And as I mentioned before, we're using Elemental to store the data sets. Inside Alchemist, we're busy incorporating support for Scala-Pack as well. And so far, development of Alchemist has only been on Cori, which is a supercomputer. Of course, what would be really useful is to run this on clusters in the cloud. To do this, we need to put Alchemist inside a Docker container or use Kubernetes or something, and that's something we're working on as well. And hopefully that's going to make it more accessible to people who want to run this on clusters or on the cloud. There are some limitations, of course, using this approach. One is that you need two copies of data in memory. The problem here is that you can store it in one format that's appropriate for Spark, let's say the index row matrix, but that's not going to be appropriate for Alchemist or specifically Scala-Pack or Elemental. So you need to store data in the required formats. As I mentioned before, if you have Spark and Alchemist running on different nodes, then you need to send the data back and forth. And this is, of course, subject to network disruptions and overloads. A big problem with MPI in general is that it's not fault tolerant or elastic. So earlier we saw a talk on Project Hydrogen that kind of addressed the same issue. Was it just a necessary constraint of MPI? There's also, I mean, there are a bunch of libraries out there for linear algebra using MPI. There are fewer libraries that actually do machine learning in MPI. There's one called Matic that's available, but there are surprisingly few libraries out there for machine learning specifically. One limitation that we have that's specific to Cori is we're not able to run Alchemist and Spark on the same nodes. That's something about the Spark implementation that's running on Cori that just doesn't like that. So we need to, we're still trying to address this issue so that we don't have to transfer quite as much data over the network. Future work, so this approach also allows us to interface Spark with other libraries. So 2 other projects that are being used for distributed computing are Cray Chapel and Apache Reef. We want to reduce the communication costs using locality and reducing the amount of data we have to transfer. And specifically, if your network has some interconnect that has a particular network protocol, then we should be exploiting that network protocol because TCP/IP is going to be more expensive in that case. Running Alchemist as a network service would be useful if we can run this have Alchemist running on every node, and if it's just running on a node, it's not going to be taking up resources unless you call Alchemist specifically on a certain number of nodes, and then it spins up and you can use it. And if it's running on the whole cluster in the background, you can also use nodes that aren't being used to perform some basic fault tolerance and elasticity. Okay, that's it. I want to thank Cray and DARPA and NSF for financial support. We've got 2 papers coming up that have already been accepted. And we've got a GitHub repo if you want to, well, right now there isn't too much on there. I'm going to put some stuff up later. Okay, thank you. Any questions?
Thank you. Great talk. I noticed that in the scalability, that when you went to 308 nodes, it actually sped up. I mean, the time was actually greater.
308 nodes, yes. Time was greater. Oh, that's where it's going to be. The reason here is that, so the yellow is the time it takes to load the data from HDF5. So the more nodes you have, the faster that's going to be. The green is the time it takes the data to get sent back to Spark. So that's the results get sent back to Spark, and we have Spark running on only 2 nodes. So you have 308 nodes communicating the data to just 2 nodes. And it's just, that's a whole lot more communication. There's a lot of overheads. The 2 nodes can only take so much data at a time, so that's why it takes a little bit longer. And overall, it balances out, but it's a little bit more.
I was wondering, is there some kind of a heuristic to say for a problem of a certain size that an optimum number of nodes is X, for example? We ran, one of the papers I just had up, we ran some communication experiments. They were kind of inconclusive. We need to run more detailed communication experiments to get a good idea of if you have this number of Alchemist nodes and this number of Spark nodes, just how long is it going to take to send data back and forth? So those experiments, we did some initial results, but we need to do a lot more testing for that.
Great talk. I'm trying to understand where the benefit come from. How much of this is a platform issue versus library issues, MPI versus Spark? For example, if I do the same algorithm on Spark, and maybe even if I say throw GPU in there, would I still suffer maybe because of shuffle versus MPI? I mean, what is the benefit in this? That's what I'm trying to understand. How much of it is the MPI platform versus Spark platform as compared to the math libraries not mature enough in Spark? At some point?
So it's the main issue is the bulk synchronous model that Spark uses, where communication only happens at the end of stages. So for these computations, you need to have processes communicating with each other quite often. In Spark, you can only do it at the end of stages, so there's a whole lot of waiting time. So just going back to some of this, probably I should just probably refer you to that original case study paper, but some of the issues are specific to Spark, to platforms. You see here at the bottom is task start delay, schedule delay, task overheads. These are platform-specific things. So it's not something where you can tweak something in MLlib and it's going to run great. It's something specific to Spark. And we would just want to bypass those Spark-specific things by calling it MPI-based routines.